Kia ora koutou, nau mai, haere mai. Welcome to lesson 10 for introductory physics. So this lesson, as I said on the stream site, is going to be a little bit different. It's going to be a little bit of a hint as to how to approach physics problems in general. And then I'm going to work through 4 different examples on the document camera, narrating as I go so that you can hopefully get a feel for how I tend to approach physics problems in general. I'll be using examples that relate specifically to the forces problems that we've covered. That's why the lesson is called forces problem solving. But the idea is the thought process, the approach to solving problems applies equally to any physics problem. You should always follow these sorts of steps. I'm hesitant to call them steps because they're not always done in order according to exactly how I state them. Just more hints and tips, I guess, is the better way to describe them. So the lesson does have some slides to start with, but they're just some hints about how we approach physics problems. So to start with, whenever you read a physics problem, read the given scenario carefully, try and visualize it if you can, make sure you understand what is going on in the scenario. So in the whole picture, not just your system, in the whole big scenario. Is it clear what is happening? Do you actually understand what the scenario is describing? Can you visualize it? Is the scenario describing a static scenario? I realize that says scenario twice, but anyway, is the system or is the thing that we're interested in, is it static or is it in motion? If it's a static, that means everything's at rest relative to each other. That's fine, that's good. We now know some information. We know there's going to be no net forces on it because everything's static. We also know velocity is 0 and so on. If there is motion, is it constant velocity or is it constant acceleration? Or is it varying acceleration, in which case it might be too difficult for us to even approach. But if it's varying acceleration but in sort of blocks of constant acceleration, then we can deal with that. We just have to break our system down time-wise into a system where it's got some acceleration of one rate, and then it changes to a different system with a different acceleration. And that way, while we're looking at it, we're only ever working with a single acceleration. So depending on the type of motion, constant velocity, constant acceleration, or varying acceleration, which we would only ever work with if we broke it down into sections of constant acceleration. Depending on that, we can then know whether we're going to need to deal with kinematics or just with our really simple constant velocity equations. Is there a specific intention being acted out in the scenario? Like, is someone trying to move something or stop something from moving? This is sort of related back to that first point of, do you understand what's actually happening? The reason I've put this in as a separate point is specifically for when we're talking about friction. If someone is trying to move something or stop something from moving, that means there are forces attempting to cause motion and there may be friction even if the system is at rest. And finally, what is being asked about the scenario? Do you need to know a force, a time, a mass? Are you looking to compare a couple of things? What are you trying to figure out? You should always have an idea of what the question is actually asking, as well as an understanding of the scenario in full. So that's what I'll do just from reading the question. The first time I read through the question, I'm thinking about all of these different things. What kind of motion, what kind of forces, what kind of purpose is there? What's happening in the scenario? Why is it happening? And what are we actually looking for about the scenario? Then the best first step after that is often to draw a sketch. I've said that you only really need to be able to draw free body diagrams if you are comfortable doing more complicated sketches. And by more complicated, I don't mean detailed. I just mean rather than dots as your objects, you might draw a box or you might draw a line representing a string or a circle for a pulley, things like that. You might draw a parabola showing the path of a projectile. Things that are simple but a little bit more detailed than the dots for our free body diagrams. So if you could draw a diagram, that's great. If you have a static system, so there was no motion, if our answer to that question about motion was that there wasn't any, then free body diagram is probably actually all you need. But if you do have motion, you should often sketch the motion out. It's beneficial just to get an idea of what's going on. Then you need to define your frame of reference. Is the motion involved? Actually, not just the motion, the forces and the motion. Are the forces in motion, are they in 1 dimension, 2 dimension, or 3 dimensions? Once you understand which dimensions you are working with, you can then decide what your axes are going to be called. You might call them X and Y, or just X, or just Y, or X, Y, and Z if it's three-dimensional. Once you've figured those out, then you figure out which direction each one is pointing and which way is positive or negative. So this is something we've been practicing right through since kinematics, so hopefully you're all pretty practiced at that. Once you've defined those, you then will generally know the origin. That's part of setting up those frames of references, the point where they all cross, that's your origin. And is there time involved in your scenario? If there is motion, there is usually time involved. If it's a static system, so if something is not moving at all, time is not usually relevant. But if there is time, so if there is motion and thus time, then you'll want to set your time origin as well. That is officially part of your origin, it's part of your frame of reference, but sometimes we don't need to worry about time, so I just put it in there as a separate point. Think about when the stopwatch is starting, this theoretical stopwatch that's observing this system, when is it starting? Determine the relevant laws or equations. With an understanding of the scenario, the relevant forces and motions involved, you now can think about what laws and what equations we have to work with. So do we know that the system has a bunch of forces on it? Cool, we're going to be thinking about a net force, and that means we're going to be thinking about Newton's second law, maybe his first law, maybe his third law. So we need to write down any equations that might be relevant. Do we know that we've got constant acceleration? In which case we don't need the do we know that we've got constant velocity? Then we don't need the kinematic equations. We can just go straight to our velocity equations of v equals change in displacement over change in time, and rearrangements of that. Do we have forces due to gravity, due to friction, due to normal force? What kind of forces are there, and what rules and equations have we got for those? So thinking about all of those, making sure we've covered all the bases there. Remember, as you're doing that though, that we often make a bunch of assumptions. Are we making any in this question? Are we ignoring air resistance, for example? Are we assuming that a person is moving with constant velocity, even though in reality they might be starting or just sort of varying slightly, as humans tend to do when they're walking? So are we making these sorts of assumptions? You can't confidently state your results if you haven't thought about these assumptions. Unless you've actually considered them, then you don't really know if your results are going to be anywhere near what they will actually be. So we don't always state them. That's why they're implicit assumptions. We don't often write them down in full. But if there's an assumption that you think is questionable about this system, then you should include it. Then we can move on to writing the question or scenario in terms of our frame of reference. At this point, we need to think about the system. So remember, the scenario is different from our system. So now we need to think about specifically our system. What part of our scenario are we concerned with? Are we concerned with just a ball, or are we concerned with the soccer player and the ball? Are we concerned with just a car, or is our collision between a car and a truck, we're concerned with both vehicles? What is our system? Once you know the system, then you can think about all of the forces, and that's where we need to be thinking about Newton's third law in terms of action and reaction forces. Figure out which forces are being applied to the system by things outside the system. Those are the relevant forces for our analysis. Once you know which forces you're working with, you can decompose them all along with any velocities and accelerations, because those are all vectors. And once you've got your frame of reference, you need to decompose everything into that frame of reference. And as I said, if we're dealing with something that has different acceleration stages, or possibly some other scenarios like we saw when we looked at projectile motion. When we talked about projectile motion, we talked about the idea of launching something not from the ground and not from the peak, sort of part way up and at an angle. In that case, it was often simplest to actually divide the motion into two parts. Part one being from where it was launched to the peak, part two being from the peak back down to the ground. And so it's not just when the acceleration is varying that you want to break it into stages. There can be lots of reasons. So think about that. If you are going to do that, be very clear, define the different stages of the motion. And then, after all of that, you are now ready to do the maths. So this is where a lot of teachers will jump in. They'll just jump in at this point. They've done everything I just talked about. They've done it in their head because they've done it so many times. They're so used to looking at a system, and without really even consciously making the process, they've already figured out the frame of reference, they've figured out the forces that are involved, they've figured out what the system is, they've figured out where their origin is. They've done all of that, and they never really state it. Sometimes some good teachers will, but a lot of them just skip over it. So if you've done physics before and you often found yourself confused, it was probably because all of that stuff we've just talked about was missing in the explanation that was given. Once you've done all of that, you've got your equations, you've got your values all decomposed, then you are ready to solve the maths problem. And sometimes these math problems can still be quite difficult, so you do still need to be prepared to do a decent quantity of maths. It's not physics instead of maths, it's physics and then maths. So you need to be able to do both of them. So yeah, don't rush into this math step. Make sure you take the time, think about all those things that we've just been saying, and make sure you are happy with the physics of the scenario. And then, only then, should you do the maths to figure out your numerical results. But most importantly, despite everything I just said, there is no one way to do any physics problem. Physics is about problem solving. That means being given a bunch of information, thinking about what we know, about the system, about the world, about our laws of physics, about everything. Think about it all and try and figure out how to solve the problem. That is our goal, and there's no one right way to do that. As we saw with kinematics, I'll go back to that idea of a projectile motion where you're launching something from halfway up or part way up. Yes, you could break it into 2 steps, and I showed you how to do that. You could also do it, I think I might have included this in the video, you could also do it by solving a quadratic equation and doing a single mathematical equation to represent the whole system and solve that, which is slightly more complicated for maths, but slightly less complicated for the physics because there was a bit less in terms of breaking down the different stages and things. So there's no one right way to do it. There is just the goal of taking everything you know and putting all the different parts together. And that includes figuring out which parts are actually relevant. There are plenty of times where you'll be given a question with some extra information that ends up not being relevant at all. I think there was one when we were talking about gravity where we gave you the mass of an object or the horizontal velocity and asked you how far it falls, how long it takes to fall down a cliff. Horizontal velocity is irrelevant because it doesn't affect that vertical velocity. So it ends up being a little trick, a little extraneous bit of information that you don't actually need. So determining that relevant information is important. And we don't include those sorts of tricks just to be tricky. We include them because in the real world, you are often going to have extra bits of information and extra things that you know that you don't really need in order to solve any given problem. So with all of that said, I'm now going to solve a few problems. These by necessity aren't really long, complicated and terribly involved. They are slightly on the simpler side in terms of what we could do with the content you know, but they are probably on the harder side for what we'll generally assess you on in terms of exam questions and stuff. So I will work through these. There are 4 of them. The solutions are not in the slides. The slides just have the questions, but the solutions obviously are going to follow shortly on this document camera. So the first example is a book on a slope. We have a book at rest on a gentle slope of 10 degrees to the horizontal. The book has a mass of 150 grams. The coefficient of friction between the book and the slope is 0.25. Determine if the book is at rest or slides down the slope. So that's the first question. Is the book at rest or does it slide down the slope? The second part of the question is the slope is then changed to 49 degrees. If the slope is 5 meters long, how long will the book take to slide down the slope? So as I was reading that, I've already started making some decisions in my head. I've said, all right, we've been told the slope. My frame of reference is going to be fixed to that slope, not to the horizontal. That slope is the important thing, so that's what we're going to fix our frame of reference to. We've been told that the book has been given a mass and we've got friction. So it's like, okay, cool, we're going to have a weight force, we're going to have a normal force. The normal force is not going to be the same as the weight force because remember the normal force is perpendicular to the slope. The weight force isn't, so the normal force is going to be different. That means there will be a weight force component pointing down the slope. That means we're going to have some friction. I'm going to work through all of this. Don't worry, this isn't my solution. I'm not just going to talk in the little corner video up in here. I am going to work through this all. But I've just been thinking through some of this already as I read the question. The first part of the question then is, does the book slide down the slope or is it at rest? And hopefully, as I read that out, your brain is going, okay, that just means we need to know if the net force is 0 or not, because that's the answer. is the net force 0? If it is, then the book is at rest initially. Right? We're told a book is at rest. That's the first 5 words. A book is at rest. So if the net force is 0, there's no acceleration, the book will stay at rest. If the acceleration is more than 0, so if there is a net force, then the book won't remain at rest. And that's the question. So that's what we're actually looking for, is the net force 0. And remember, that was one of the things that you should be doing in your first read through, is think about what they're asking. So that first part of the question is actually asking, is the net force 0? Second part tells us the slope has changed to 49 degrees, and then it tells us how long the slope is and asks how long the book will take to slide down the slope. Because they're telling us the book is going to slide down the slope, we can assume that the book is no longer going to be at rest. So it is going to have a net force. We don't know what it is yet. That's the point of solving the maths soon. But we can assume there is going to be one. Once we know that net force and thus the acceleration, then it's just a kinematics problem. If we know the acceleration down the slope and we know how far it has to travel, that's a kinematics problem. So that's my first thoughts. That's before I've even written anything, just from reading the question. So let's jump over to the document camera and let's work through this properly in full. First thing I'm going to do is sketch a little diagram. We have a slope, which is at 10 degrees to the horizontal. There's a book sitting on our slope. That's our book. The book has a mass of 150 grams, which I will just write straight into SI units. So that's a good practice, a good habit to get into. We're told that there is a coefficient of friction of 0.25. So that's happening here, right? In between them, I'm just going to write it over here. 0.25 is our coefficient of friction. And that's all we've been told. That's what we've been told, and we're asked, does the book slide down the slope or does it remain at rest? So at this point, this diagram isn't really necessary. You might just be happy to write these 3 bits of information down. Regardless, drawing a free body diagram is a good next step. Before the free body diagram, we need to think about our system and our frame of reference. So our frame of reference, I already said, I'm going to fix it to the slope. So this is horizontal and this is vertical, but I don't care. I'm going to make y and x be up away from the slope as my y and down the slope as my x. So that's my frame of reference. I'm going to call this positive and I'm going to call this positive. The positive y, negative y, won't be involved in the motion of the book. The motion of the book will be one-dimensional. It will only ever move up and down this x dimension, x-axis. Because we know that that book's not going to float off the slope or go into the slope. It's only ever going to move along the slope. That's why we choose our x-axis as being along the slope. So that's our x-axis. Our motion is one-dimensional, but the forces are two-dimensional. We do have forces in the y dimension, so we do need to include that dimension in our system analysis. The system itself, our system is just going to be the book. All right, so the system is just the book. That's all we have for our system. We don't want to include the slope, because if we include the slope in our book, then we can't include the normal force in our analysis, and that's how we figure out the friction, because the friction is a force by the slope onto the book, as is the normal force. They're different forces. One's from the slope not letting the book sink into the material, whatever the surface is, and the other one is from the roughness of the surface slowing the book down as it tries to slide, or preventing it sliding, or slowing it down, depending on what happens. So we do have forces from the slope onto the book, so the slope can't be part of our system. So that's our frame of reference, that's our system. Now we can think about our free body diagram. And what I'm going to do is I'm not actually going to draw the free body diagram in the same angle as I've done it there. I'm going to draw my normal forces being straight up, because that's now in my y dimension, and my x is this way, that's y. So we've got the weight force is going to be at an angle, and this angle is going to be that same 10 degrees. To think about that, you may need to stop and think about the geometry for a moment. But if the weight force is straight downwards and this is perpendicular, then by simple geometry, this right-angled triangle here is the same as this main big right-angled triangle. That means this is also 10 degrees. So we've got 10 degrees between our negative y-axis and the weight force. There's our weight force. We've got the friction force as well. That's the only other force that can be or will be acting on it. We know that there will be a friction force. The question is really asking, is the friction force big enough to make our net force 0, or is it too small? So we don't know exactly how big that is yet, so we can't really draw it to scale. So that's our friction force, Ff. And those are our 3 forces. Normal force and friction force are already according to our frame of reference, so they're fine. So we don't know exactly what they are yet, but we do know that they are equal. They are written in our frame of reference already. So Fn is equal to some value. We don't know what it is, but it's in the positive y direction, and it's newtons. The friction force is some value again. It's in the negative x direction, and it's in newtons. The weight force we're going to need to decompose. So we want to decompose that into a parallel component that's often represented by a couple of little lines, and a perpendicular component, which is often represented by a little upside down T. That's because we have 2 parallel lines or perpendicular lines. That's literal graphical representations, but they're quite common to see those symbols. So those are our forces that we need, our decomposed forces that we need to know. We can see that this part is going to be positive. We're going to get a positive x and a negative y. So we're going to have the parallel component, which is along the x-axis, parallel to the surface of the slope, and the perpendicular one, which is into the slope. Parallel one is going to be positive on the x-axis, and the perpendicular one is going to be negative on the y-axis. So I'll put a little plus in there for our normal force as well. So we don't know what all these values are yet, but we do know that each of them now, if we break this down into 2, the weight force down into 2, each of them will be in either the y or x axis. And that's what's going to allow us to determine if it has a net force on it. We also know that the normal force has to be equal to the perpendicular component of the weight force, well, equal and opposite, because we know the book is not going to have any motion in that y dimension. We know it's not going to go upwards, it's not going to happen. So that means that we must have these 2 are going to be equal, right? Their magnitudes are going to be equal. And that's just thinking about the laws of physics. We know that's going to happen from experience and from just from watching the world and understanding how books sit on slopes. They don't suddenly fly off them. So there is sort of what we know. We have the weight force is going to be equal to mg. We know that. That's from what gravity is, how gravity on Earth is defined. So that's fine. We also have that the normal force is going to be equal to mu. The friction force is going to be mu times the normal force. So we need to figure out the normal force to get to that. The normal force is going to be equal and opposite, as we said, to this perpendicular component of the weight force. So we've sort of got everything we need to know. Once we know all of that, we can then compare this friction force and this parallel weight force and see if we can get enough friction. So let's do that. So we're moving on to a bit of math now. We might go back to doing some physics, but for now we're moving on to doing a bit of math. And the math we need to do is this decomposition, this vector decomposition. So if we have this right angled triangle, I'll redraw it just to be really clear. We have this right angled triangle. Here's our F weight, which is equal to mg. And we're looking to decompose it into a perpendicular component and a parallel component. So that's our perpendicular, and that's our parallel. This is 10 degrees. This is a right angle. That's just simple SOHCAHTOA. So we now can calculate these. If perpendicular, that is adjacent to our angle, so it is going to be FW, the hypotenuse, times the cosine of theta, which is mg cosine of 10 degrees. And if you've got your calculator, you can check that, that comes out to, m is 0.15, 150 grams times 9.8 times the cosine of 10 degrees. That comes out to 1.4477. One of the other things that I haven't actually mentioned, because it's part of the math and I tend to brush over that a little bit, especially during those hints I gave you, don't round while you're working, round at the end. So I've got 5 significant figures here. That's more than I'm going to need because everything in the question was given to me as 2 SF. So at the end, I'm going to round my result to 2 to match all the values that I was given. But while I'm doing the working, I'm not going to round. I'm not going to make that 1.4 because then we're losing this extra information and that might actually affect our final result. So there is our perpendicular weight force. We're now going to move on to the horizontal or parallel weight force. I shouldn't say horizontal because it's not horizontal, it's along the x-axis. So FW parallel, that is equal to mg, 1.15 kilograms times 9.8 times the sine of theta this time, sine of 10 degrees. And that again, trigonometry, we've got this is opposite. So we're going to have sine of the angle. So sine of the angle times the hypotenuse will give us this side. So we have that times the sine of 10 degrees. So it's the same formula, but with the sine in there. And that tells us that we have 0.255, I'll go 26, keep it at 5 SF while I'm working. That's not a rule. Don't hear me say 5 SF twice and then stick to always doing 5 SF. Just write more than you need is the point. You could write, in fact, I'll change that just to be really clear. I'm going to do an extra one. I'm going to go to 3 this time for newtons. There we go, 6 FF on that one. Doesn't matter as long as it's more than I'm going to need. So those are our two components for the weight force, parallel and perpendicular. And now just to, I wouldn't normally do this, but just to be really clear, I'm going to draw the free body diagram again. And now I'm going to draw on what we know. So we know that the F weight parallel is in the positive x direction, and that is equal to 1.4477 newtons. And we know that FW perpendicular, the weight force in the y direction of our frame of reference, is equal to 0.255263 newtons. Note that I'm not technically writing this correctly. If I was to write this in full proper notation, I would write equals negative 0.255263 y newtons, because it's in the y direction and it's a negative one, as I sort of hinted at when I did this this bit up here. But I don't really need to do that if I'm attaching it to a free body diagram, because this shows you it's in the negative y direction by this. So I only need to give you the magnitude and then the direction is on the free body diagram. But if you wanted to write it in full mathematical notation, you'd write that. We then also know that we have a normal force upwards. We haven't technically calculated this yet, but we do know that it's equal and opposite to this. That was what we stated. That was our determination based on the fact we know the object is not going to fly up off the slope. So this is going to be equal to I've done those the wrong way around, I just realized. Those are back to front. I haven't rehearsed this enough, so there we go. Those are back to front. Real mistakes, just like you'll do in the real world as well. So that's 1.4477 newtons, and that is 0.255263 newtons. Okay, so there is our new free body diagram, and we know that this is going to be equal and opposite to the perpendicular weight force, and that's going to be 1.4477 newtons. And that way we have no net force in the vertical direction, and we're not going to get any motion in the vertical direction, which is what we know. We've used that fact that we know that in order to calculate this normal force. Now we have to figure out the friction force, because that's the only one we don't have left. We know perpendicular and parallel. We know normal because it's equal and opposite to perpendicular. Now we can figure out the friction force. Sorry, I just dropped my Vivid lid. I'll just pick that up. So now we can figure out the friction force. We do know the friction force is equal to mu times Fn, and we now know Fn, and we were already told mu, so that is 0.25 times our normal force of 1.4477 newtons, which gives us 0.25 times 1.4477 is 0.36193 newtons. So there is our friction force. Sorry, I should say maximum friction force. That's what we've calculated, our maximum friction force. Now remember the rules for friction. The maximum friction force will occur if it's moving, but if it's at rest, then it will only take as much friction as it needs to stop it moving, if it can. So in this case, the force that's trying to make it go down the slope is this one, 0.255263 newtons, and the friction can be up to 0.36193 newtons. So it can have up to that much if it needs it, and that is more than the force that is trying to make the book go down the slope. So therefore it can have enough friction and it will stop it from sliding. So this will not be the friction force. Right? It won't get that high because it doesn't need that much. If the friction force was that, then that would be bigger than our weight force and the book would spontaneously slide up the slope, and that makes no sense. So instead we have actual friction. So the actual friction is therefore going to be equal and opposite to the parallel component, because it's just going to take what it needs, and that is 0.255263 newtons. We didn't even really need to do this last step. I didn't actually need to write this exact value down because the question was simply, does the book slide down the slope or not? The maximum friction is more than the force that's trying to make it slide down the slope. So book stays at rest. All right, there's no value, there's no quantity that we were asked to provide yet. That is our answer. Book stays at rest. So that's the first part of that question. So it's a couple of pages of working, but as you may have picked up, a lot of physicists, when they're answering a question like this, would just say, well, this is the normal force, this is the weight force, therefore our maximum friction is this, and therefore we have enough friction. And they would skip that whole start bit that I did about determining our frame of reference and figuring out which direction everything's in and thinking about the scenario. They do all of that in their head, and that's not very useful for you to learn the process. The next part of this question says that the slope changes. The slope is now 49 degrees. We've still got the book. We've still got a weight force of mg. We've still got a friction coefficient of 0.25. And we need to figure out how long the book takes to slide 5 meters down the slope. So we know that delta x is equal to 5 meters. 5 meters down the slope. How do we approach this? Sorry, I just realized I've drawn that off the screen. There we go. How do we approach this? It's kinematics at the end. Once we know the acceleration, then it's kinematics, and we can just plug in our equations and the known distance and the acceleration. The initial velocity is 0 because we're told it starts at rest. We're not there yet though. We have to figure out that acceleration. In the previous step where we had a 10-degree slope, there was no acceleration. Now we have to figure out what the acceleration is, and we're told effectively that there will be one because we're told it will slide down the slope. And that also matches our common sense. We would expect a book to slide down a slope if the slope was this steep. So how do we do it? Can we just take the friction force we had before and now figure out our new parallel component of the weight force? No, we can't, because the normal force is not the same anymore. The normal force will be different because the slope is different. So the normal force is not going to be the 1.4 whatever it was that we had before. It's going to be a different value, and that means that the friction force will be a different value. So not only is the slope steeper and there's more weight force in the parallel component pulling the book down the slope, but there will now be less normal force and thus less friction force. So there's more weight pulling it down and less friction holding it up. And that makes sense because the steeper you make the slope, the less it sort of grips onto that slope. Indeed, if you went all the way to 90 degrees, there'd be no normal force and no friction. The book would just fall down next to the slope. It wouldn't really experience friction. So we have to redo everything. We cannot reuse any of the results that we just had, except the formulas. And that kind of involves some of the physics, right? We said that our normal force was equal to the weight force, equal and opposite to the weight force in the perpendicular direction. And we also saw that the perpendicular component of the weight force, we saw that was equal to FW, the weight force, times cosine theta. And that's still the same, but now we've got a different theta. So we still have mg cosine theta, but now we've got same mass, same gravity, but we've got the cosine of 49 degrees instead. And that is going to give us 0.15 times 9.8 times the cosine of 49 is going to give us a normal force of 0.96441 newtons. So that's our normal force and our weight force magnitude. I'm not, again, remember this is just our magnitude. I'm not including the pluses and minuses and x's and y's that determine everything because we're just assuming it's all, well, not assuming, we are keeping in our mind, we're keeping in our head what the frame of reference is. And the y is still perpendicular and the x is still parallel. So this frame of reference is now different than it was for the previous example because the slope is different. So we've still got our frame of reference being parallel and perpendicular, but if the slope's changed, our frame of reference technically has changed, but we're treating it all very similar. The formulas will come out the same. There's our normal force, there's our weight force, that's great. Sorry, our weight force perpendicular, that's great. Now we have our friction force. So this is our maximum friction force, and it is equal to mu times Fn. Mu is still 0.25, but we now have the smaller normal force. So the friction, the maximum friction we can get is now going to be 0.25 times what we just calculated. So answer times 0.25 is 0.2411 newtons. So that is our maximum friction force. What is our weight force that's pulling it down the slope? Our weight force parallel, that is equal to mg sine theta. Same formula as we had before, but again using our new values, which I won't bother writing, I'll just type straight in. 0.15 times 9.8 times the sine of, I almost did 10 again, sine of 49 degrees is 1.1094 newtons. So we now have a weight force pulling it down the slope of 1.1094 newtons and friction force pulling it up the slope or trying to stop it sliding down the slope of only 0.2411. So now we do have a net force. And our net force is going to be, we've got Fn and Fw, they're equal and opposite, so we've got no net force in that direction. But now we've got Fw parallel is bigger than F friction. So because this is the maximum friction and it's less than the force that's pushing the object down the slope, it will experience this maximum friction. It will. So we can cross out max because that is the actual friction. Right? That is our actual friction because it will use all of it because it's the force pushing it down the slope is enough to overcome that friction entirely. So now we know this is our free body diagram. Our net force is going to be this, right? F net is going to be in the positive x direction, and it's going to be equal to the parallel component of the weight force minus the friction component. The normal and the weight force perpendicular, they cancel each other out. Again, that was one of the facts we used to solve this problem. We know the normal force and the weight force perpendicular are going to cancel out because the book stays on the slope. If it doesn't stay on the slope, then we have to think about normal force being different. But while it's just sliding down the slope as stated, we know they're going to be equal and opposite. That means that our net force is going to be equal to 1.1094, that's our parallel component of the weight force, minus the maximum friction force, which was 0.2411. And that is 0.2411, 0.8683 newtons. So there is our net force. That is the actual net force on this book as it's sitting on the slope. Now that we have the net force, from Newton's second law, we know what's going to happen. We know the acceleration that will occur because we also know the mass of the object. So Newton's second law tells us that F net is equal to ma. Therefore, the acceleration is equal to F net divided by m, which is the 0.8683 we just figured out, divided by still 150 grams, 0.150. So our acceleration is 8683 divided by 0.15. Our acceleration is 5.7887 meters per second that is the acceleration down the slope. We can now switch to kinematic mode. We now know that our initial velocity is 0. Also, as we switch to kinematic mode, we're switching to one-dimensional motion. Now we can think about our motion down the slope. Here's our book. It's got an acceleration of 5.7887 meters per second down the slope. It's got to travel 5 meters. Got to travel 5 meters down the slope, and it starts with an initial velocity of 0 meters per second. So this is pure kinematics. It's one-dimensional motion, and it's just straightforward kinematics. We've got initial velocity of that. We're going to set our stopwatch being equal to 0 when it's here as well. So we're going to start our timer there. we've got our acceleration, we've got our change in displacement as being 5 meters, and we've been given the acceleration. So now we can think about the kinematic equations that we have. And the obvious one here is delta x is equal to VIT plus a half AT squared, which you'll probably be familiar with by now, hopefully. The initial velocity being 0 means we can just get rid of that term. It just goes to 0. Right? And we have 5 is equal to a half times this 5.7887 times t squared. And now we're into math. Right? Now we are just doing math. This is just math to try and figure out t. So t is equal to the square root of, I'm actually going to just rearrange this rather than calculate and then divide. So we've got 5 times 2 over 5.7887. And now we can calculate that. And I haven't done this calculation yet, so hopefully it comes out to something reasonable. 57887 gives us 1.314 seconds. So at a slope of 49 degrees, the book will slide those 5 meters in 1.3 seconds. Sorry, I bumped the camera there. So that is the first problem. That's the second part of the first problem. It asked for how long. You would then present that. 2 significant figures, as I said right back at the start, 2 significant figures, 1.3 seconds. And that is the end of example 1. So as you can see, that was fairly involved for just a simple, relatively simple question. We had a book on a slope, did it move, and then how long did it take to slide down the slope? If you're doing that yourself, if you're not explaining it to someone else, that should be a lot quicker, because a lot of the things I was doing and writing and saying were for the benefit of explaining it to someone watching. If you're just doing this in your head, then you don't need to write all of those steps down. You certainly don't need to keep redrawing little diagrams and repeating the free body diagram after your first time. But if it helps you, feel free to do it. The goal is to make sure you keep everything in mind. The other thing you'll notice that I sort of mentioned as I was doing that is the forces. I wasn't writing them in their mathematical form. I wasn't saying this force is this much in the y direction every time. I was keeping that in my head. I was saying, we know the parallel component of the weight force is going to be in the positive x direction. It's pushing it down the slope. I knew that, and I just kept that in mind the whole time I was doing the example. And that way, when I thought about the friction, I was like, right, that's definitely going to be opposite to that parallel component of the weight force, because I already know that those two are in the positive and negative x directions. They're sort of opposite. And the normal and the perpendicular component of the weight force, those are opposite. Keeping all that stuff in mind will help you understand and visualize the system. And it'll mean when you get to the maths, you're not reliant on the maths to tell you, is this positive, is this negative, which direction is it in, which a lot of people fall into that trap, especially in one-dimensional problems. Especially in one-dimensional, they sit there and they rely on the positive and negative to tell them directions. Don't do that. Think about the scenario, think about the directions. The main reason I tell you not to rely on the plus and minus, even though it's perfectly acceptable, it will work if you do it carefully and properly. Well, there's 2 main reasons. One is it's easy to make a mistake when you're dealing with negatives, and if you get it wrong and all of a sudden the book's sliding up the slope, if you haven't thought about the physics, thought about what the numbers mean, that won't necessarily be obvious to you. But more importantly, when you move to 2-dimensional motion, you cannot rely on pluses and minuses to solve all your problems. You could decompose everything and write it all in plus x and minus x, and that gets really messy mathematically, but would theoretically still keep track of it all. But it's much simpler, and it's a bit more elegant to keep that physics in mind and make sure you understand it. That way you're using the maths as a tool. The maths isn't dictating to you what's happening. You're saying this is what happens, use the math to get a value. So that's my little blurb on that. Let's have another look at another problem. I will go through the rest of them a little bit quicker. Don't worry if you're getting a bit tired of listening to me explain these physics problems. That was just the first one. There are 3 more. I will move a little bit quicker, don't worry. The next problem is 2 objects over a pulley. 2 objects of masses m1 and m2 are connected by an ideal string which is hung over an ideal pulley. What is the acceleration experienced by the object? Firstly, a little note there. Ideal means no mass and no friction. It doesn't get stretched or deformed in any way. So basically, it doesn't really affect our consideration of forces. The reason that's important is that if the string has mass, then we have to start thinking about the acceleration of the string as well, because it will need a net force. If it doesn't have any mass, then it doesn't need a force to move, because there's no inertia there. Remember, inertia was the thing that resists motion. and the reason we need to apply a force. If it's a massless string, then it's just constrained by the objects it's attached to, and we don't have to think about the string per se. Same with the pulley. Pulleys are wheels that turn around, providing a relatively frictionless rotation for the string to pass over. If we assume that it's massless and frictionless, then there's no forces to think about, nothing to concern ourselves with, and it just simplifies the whole problem. In reality, are they frictionless? Are they massless? Not technically, but if the masses of the objects are much bigger than the mass of the string, then yes, we can treat it as negligible. If the mass of the string was 10 grams and the objects were both 10 kilograms, that 10 grams is going to be so small that the forces needed to move it around are going to be negligible compared to the forces we're dealing with, and we can actually ignore it. So it does get close to being negligible, but in reality, obviously, we do have to remember that if we did an experiment, our results might vary a bit because of these assumptions we are making. So two objects over a pulley, what is the acceleration experienced by the objects? You'll notice that we have not been given any numerical values. We know gravity, sure, but we haven't been told what the masses are. When you are given a question like this with no numerical values, your answer is going to be an equation in terms of these variables, in terms of M1 and M2. So what we're going to get out is a formula, not a numerical result. And that's quite a common thing in physics too, because it means that we can figure out this system, excuse me, we can figure out this system, and then we can put any two mass objects in and we know what will happen. We're not restricting ourselves to one version of this scenario. We're saying in general this scenario will behave in this way. So let's jump over to the document camera and work through this one. All right, first of all, our diagram, this may not have been perfectly clear to you from the description because you may not have seen one before, but essentially it's just a pulley and we've got a string that goes over the pulley. One end is connected to mass M1 and one is connected to mass M2. We then let the objects go and we want to know what the acceleration is. Right. Before we start thinking about all of the actual equations and stuff, let's think about a bit of common sense. What do we expect to happen? If we let this go and these two masses were exactly the same, we'd expect them not to move. So if M1 equals M2, then the acceleration would be 0 meters per second per second. If we let them go and one of the masses is bigger, then that mass is going to go down. Let's say M2 is bigger, M2 would go down and M1 would go up. Right, so if M2 is bigger than M1, then acceleration is not equal to 0. So that's our little common sense thing first. The reason I want to do that one first was just going back to the idea of understanding the scenario. Do we know what's going to happen? Because only if we have some idea of what's going to happen, will we really get the idea of whether our result is correct or not. So let's keep that in mind, but we'll just now sort of ignore it a little bit. We'll come back to that at the end is my point. Okay, so what's actually going on here? First of all, frame of reference. Frame of reference we can call vertical. If these masses move, it's only going to be up and down. It's only going to be vertical. They have different horizontal positions, so there is a change in horizontal displacement, but the masses themselves, sorry, I keep bumping my, my document camera stand. The masses themselves will not move sideways during our scenario. They will only ever move up and down. So technically it's a two-dimensional scenario, but all our motions, all our forces, everything is all one-dimensional. The rope is pulling this mass upwards, gravity is pulling it down, same here, pulling it upwards, pulling it down. If they move, they're only going to go up and down. So all our motion, everything is one-dimensional, but it's happening in two different horizontal locations. So we can sort of treat it as this sort of halfway between one-dimensional and two-dimensional, in that we'll treat it one-dimensionally, but keeping in mind that really there is this slight difference in horizontal position. And all that means is that the masses won't hit each other as they move. Now, let's think about what's happening with the tension force in this string. I promised you during tension I would mention another little bit of information about tension, and that's this idea of what's happening at this pulley. Remember that tension is just this force pair. If this mass is pulling down on this end of the string, then the string is pulling up on the mass with the same equal and opposite amount. And then what's going to happen when you get to the pulley? That's the question. We also know that this string over here is pulling up on this mass, and therefore this mass is pulling down on this string, this end of the string. And you can think about the string as a whole series of small sections of string. You might even want to think about it as chain links. So let's imagine that we've got chain links instead of a string. If you've got chain links and this one is attached to our object, then that object, right, is being pulled up by the chain, and the chain is being pulled down by the object. But then this next chain link is going to be pulling that first one up so that it's got no net force, and this next one is going to, oh, it's got, we don't know the net force, but it's continuing that pattern of transferring the force along. That's what the tension is, it's transmitted force. So that'll pull that one up, which will pull that one down, and then that will pull this one up, and the next link will pull it down, and so on. And so each link pulls the following one up, and the next one pulls it up, and so on. And so we get all these Newton's third law of reaction pairs all the way along between every chain link. And because every one is equal and opposite, if we think about this string as a system, remember that a system we can define as any collection of objects. So we're going to think about all of these chain links as one big system. Then all of these internal ones we can ignore because they're all equal and opposite. They're all applied to things in the system, so we can ignore them. All that matters is that end force that's being applied to the mass from the end chain link, and from the end chain link back from the end chain link back onto the mass. That's all that actually matters. And then you're going to get the same pair the other way at the other end of the string. So that's all that it's doing when we talk about transmitting the force. As it goes around this pulley, right, the same thing is happening. Right? We're still getting each chain link pulling the next one. It's just that they're now pulling them around a corner. So the force that this one is being pulled down by the next link is the same that this one is being pulled down by that link in that case. So what a pulley does, I realize that's probably not an in-depth scenario description. It does get quite complicated if you want to understand everything fully in terms of all the forces involved. But what a string does in the same way that that chain does is each part of the string just passes on that force to the next one. The tension is the transmitted force. A pulley changes the direction of that force. So this chain link here pulls this one in that direction, and then in that direction, and that direction, and that direction, and so on. So the pulley does apply some force, but all it does is it applies force to change the direction of the existing force. It doesn't change the magnitude. You're going to have to just trust me on that. I'm not going to go into full detailed explanations of why that's true. Indeed, if there is any real friction, it will change the magnitude slightly. But in our ideal scenario, the friction is zero. That just changes the direction of our force. It does not change the magnitude. So the tension on this side of the string is equal and equal. I can't say opposite because tension is both directions. The tension is equal to the tension on that side. This pulley just rotates it around. It turns it around by 180 degrees. So the upshot of all of that, you don't have to remember all this detail or everything I was talking about here. You can forget all of that if you want. If it didn't make sense, just forget about it. The important thing is that the tension is transmitted force, and the pulley changes the direction of that transmitted force, but it never changes the magnitude unless friction becomes noticeable, and generally we'll ignore that in pulley systems because it gets messy, right? So tension can change direction as you go over a pulley, but not change magnitude. So with that in mind, now let's think about our whole system for the purposes of solving this problem. We've already said that we have these two masses. They're connected by a string over a pulley. What happens if we take the system as being both of these masses? If we take the system as being both of these masses, then we're going to have weight force in between them, but we've got this tension force that leaves this mass and then comes back to this mass, but in a different direction. And it's kind of this messy part of having two ends of a scenario connected by a string, but not really doing the same thing. So instead, it gets a bit messy. Instead, what's better is to almost think about this as two separate systems. Right? Think about M2 system, and then think about M1 system separately. Right? So think about these two separate systems, and we're going to do that. Let's think about the forces that are happening on M2. Right? We've got a string, and that string is providing a tension force, and then we've got a weight force. That's it. That's all there is. Tension force and a weight force. We don't know the tension force. We don't know if it's equal and opposite to the weight force. It's only equal and opposite if the net force is 0 and if the acceleration is 0, which only happens if m1 equals m2, and we're not told that, so we can't assume that. So instead, let's think about what the forces are involved. We have tension. We don't know what it is yet, but that is equal to the mass times acceleration. Acceleration to m2a2. I won't put subscript on tension because we said it's the same everywhere. This acceleration, that's just Newton's second law, F equals ma. This acceleration, we don't know what that is. We know that if the masses are the same, it'll be 0. If they're not, it won't be. What's it going to be? How is it going to vary compared to the first system, M1, A1? How is A1 and A2, how are they related? Now this bit, there's no formula here, there's no equation, there's no rule you can always follow. This comes back to thinking about our system. If we have these two masses, M1 and M2, connected by this string, and if M2 accelerates, let's say it goes upwards at some rate A, then if this string is never changing length, that means the distance between these must always be the same, and this one must also accelerate at A but downwards. So hopefully what you can see is that no matter what A2 is, A1 is going to be the opposite, equal magnitude, opposite direction. So A2 is equal to negative A1. And again, that doesn't come from any formula that you can just regurgitate. That comes from thinking about the system and making sure you understand what would happen to the system in different scenarios. In any scenario, that string is never changing length, and therefore the acceleration of either object will always be equal and opposite to the other object. So now we've actually got a bunch of formulas. We've got the weight force on the first object is equal to mg. It's F net, not tension. I shouldn't have written tension there. I just realized. The net force is equal to m2a2 and also equal to m2a1, which is equal to negative a2. So the net force tells us our acceleration, but we also know that the net force comes from the weight force and the tension force. So the weight force is m2 times g, and the tension force we don't know, but we just know that it's always t. So we have the net force on the second object is equal to the, we'll call weight force. I've skipped over a step, and that's why I keep hesitating, and I'm regretting skipping over it. And that is the definition of our frame of reference a bit more clearly. So I'm just going to go back and add that in. And that is, this is our y direction, this is negative downwards, and this is positive upwards. So if our acceleration of one of them was in the positive direction, if that was positive y, this would be negative y. Vice versa, if this one went down in negative y acceleration, this one would have positive y acceleration. And now that means that our g is going to be negative 9.8 meters per second because we have a negative is downwards. F net 2, we don't know if it's going to be positive or negative, but we do know that it's going to be F weight 2 minus, or plus, I should say plus, because we're doing a one-dimensional frame of reference, so plus and minus will tell us the direction, plus the tension force. Tension force in this case is upwards, right? So tension force is upwards. We've got a positive. This one will end up being negative because G is negative. So that negative is already in there, hidden inside the G. F net on the first object is the exact same formula, but now with FW1. The tension, as I said, is the same because the tension in the rope everywhere has to be the same. It just changes direction, and on both sides, it's pulling the object up. So that's our formula for the net force for both of them. What we don't know is the tension, and we've been asked to figure out the acceleration, which means we need to get the, we already know the acceleration of each object is going to be equal to F net over the mass, right? We can divide by mass, so F net over mass, which means we can just take this and divide it by the mass, and that'll give us the acceleration. But if we do that, we aren't actually answering the question properly because we've got this tension force and we don't really know what that is yet. We haven't said what that is. So it's kind of skipping the important step of writing it in terms that we either know or are given. We were given M1 and M2, even though we don't know the quantities, we were told to use those terms, and we know gravity. So that's really all we should end up in. So how do we figure out tension? Let's call this equation 1 and this equation 2. And we know that the F nets are equal to M2A2 and M2A1, where of course A1 and A2 are just opposites. So what I'm going to do is I'm going to rewrite it, and I'm going to call A2 just A, and I'm going to call A1 negative A. Actually, I'll do it the other way around. I'll call A2 negative A and A1 positive A. So for system 1, we have M. I've written M2 there. M1A1. M1A is equal to M1G. That's our weight force. M1G plus the tension, and we have M2A. That's here. F net M2A, but negative now for negative A is equal to the weight force on the second object, M2G plus tension again. So what we can do is we can see that tension, we can use either one of these. I'm going to use this first one. We can use either one of these and rearrange it to find tension. So tension is equal to M1A minus M1G, minus M1G. Remembering that G is negative in there, but yeah, we'll leave it as negative, M1G. That's our tension force. What I'm going to do then is put that back into the second equation. So we get minus M2A equals M2G plus this whole thing, M1A minus M1G. Because now tension we know is equal to this, so we'll put that into here. So this is just algebra. This is just rearranging equations and substituting them in and so on. Once we've got that equation, so I didn't really state it, but once we got here, we're pretty much just doing maths. This is just maths now. Everything else we knew. Everything before that was the physics. So now we can rearrange this, and we get A. We just divide the whole thing by, actually we need to bring this A over this side. We can just get rid of these brackets because it's plus these brackets, so these brackets aren't changing anything. Let's take this term over the other side. We get negative M1A minus M2A equals M2G minus M1G. Right. We'll notice that we've got 3 negative terms and 1 positive term. Purely for my own sanity, I'm going to divide by -1 or multiply by -1, either way. I'm going to make the negatives positive and the positive negative. So M1A plus M2A is equal to M1G, that's now positive, minus M2G, that's now negative. And the reason I did that is just to make it a little bit cleaner, because what we're going to do now is factor out the A's and G's. So we get A times M1 plus M2 is equal to G times M1 minus M2. And now we can just divide by this whole bracket. Just going to divide by that whole thing. Divide by that, we get A is equal to G M1 minus M2 over M1 plus M2. And that is the answer. That is the acceleration that these two blocks will experience in terms of gravity and their masses. No other information is required. So that is the answer. And as I said, we were given a scenario with no specific quantities, only these values in terms of variables, M1 and M2. So we need to give our answer in terms of those, and that's going to be a formula. The other thing I mentioned that I would come back to right at the end of this question is this little assumption at the start. We said if M1 is equal to M2, the acceleration is going to be 0. Does this formula agree with that? If M1 and M2 are the same, then M1 minus M2 is 0 because they're the same. So we get 0 times gravity, acceleration is now 0. It doesn't matter what the bottom is because the top is 0. If M2 is bigger, then that means that this term here would be negative, but this term here is also negative because it's gravity, and our mass, our acceleration would overall be positive. And remember that we said that A1 is the positive direction. So if A is positive, then A1 is going upwards, which is what we would expect. So everything agrees with our little common sense stuff at the start. Again, that was probably more complicated than anything you would get in this course. These questions are a little bit on the harder side, but if you can follow them, and especially if you can figure them out yourself, then you'll be well on the way to solving any kind of problem we're going to throw at you. That one, as I said, was a little bit different in that we didn't give you values. We gave you these symbols, M1 and M2, and you needed to give an answer in terms of those. So there are 2 more problems. We're almost there, halfway through the examples now. Example 3, pulling luggage. So this one, there's nothing too new here. This one will be quite a quick little example. Let's again jump over to, actually before I jump over to the document camera, let's read the question. Person is pulling wheeled luggage by a strap. The luggage has a coefficient of friction of 0.11 with the floor and a mass of 15 kilograms. If they pull so that the strap makes an angle of 18 degrees with the horizontal, what is the tension in the strap? Okay, so another question involving angles, this time on the strap. So we have to think about the whole suitcase. The suitcase is our system. All right, we want to know the tension in the strap. There's a tension pulling on the strap. The strap is this is rolling along the floor. We have a coefficient of friction of 0.11, which is low because it's got wheels. This is at an angle of 18 degrees, was it? 18 degrees. We've been told the mass is 15 kilograms. And we know that the motion is horizontal, right? The velocity is purely horizontal. The person isn't pulling it off to lift it up off the floor. We're going to have a weight force, we're going to have a normal force. The trick here is that the normal force, even though the weight force is purely vertical, the normal force is not going to be equal and opposite to the weight force because this tension force is going to have a vertical component. So they're going to be lifting part of that mass up. Right? So they are providing part of the opposition to the weight force. So that's the scenario. Person pulling on this luggage. Our system is just the luggage itself, and we want to figure out the tension provided by the strap. The other end of the strap is attached to the person, but we don't really care about that because, as I said, the tension is the same everywhere. So how much tension is in the strap? Let's define our frame of reference. I'm going to stick with the standard horizontal and vertical X and Y. Whenever I draw a frame of reference and I just write one of the X's or Y's, that generally means the positive direction. So positive is the direction that's being pulled, and positive is vertical upwards. Now, there's an important step that hasn't been stated, and this is where thinking about the scenario is very important. We have not been told a velocity. We have not been told an acceleration. All we've been told is the sentence, a person is pulling wheeled luggage by a strap. That's all we've been told. In that case, you have to make an educated guess as to what the system is actually doing. If they're pulling it, they're clearly moving. We haven't been told an acceleration, so we would assume there is none. So, and this is an important thing to write down, whenever you make an assumption that isn't one of our standard implicit assumptions, when it's an assumption specifically about the scenario, we're assuming that the system is moving at constant velocity. And the reason that that's important is that we literally cannot solve this problem without it, because moving at constant velocity, that assumption tells us that the acceleration is equal to 0. Therefore, the net force is equal to 0. So we know, as long as that assumption is true, that the person is moving at constant velocity, that the net force will be 0. Is that assumption a good one? In reality, people do not move at constant velocity. I've already talked about this, the idea that as you walk, you sort of have this sort of jump in your step, this little bump and constant back and forth accelerations and stuff. It's messy. It's not this nice, clean, constant velocity system that we would have in a theoretical scenario. But if we're just thinking on average as this person is walking, then we can treat it as a constant velocity, and we can figure out this constant tension in the strap with the idea that it's just some sort of time average. It's the average over time. So we might think about it as a time average velocity and therefore a time average tension in the strap. So it's perfectly acceptable to make this assumption as long as we remember it. Because if they asked us at some instant what's the tension in the strap, we really don't know, because we know that that person's velocity is actually going to be changing constantly. That said, let's continue on. What is the net force? What is the tension in the strap? We know the net force is 0. Let's draw a free body diagram according to our frame of reference. The weight force is straight down and it is equal to mass times gravity. The normal force is straight up, but it is not equal to the weight force. You wouldn't normally write that in. I'm doing it to remind you all. It's not equal and opposite to the weight force. We have a tension force that is at an angle of 18 degrees. And we have a friction force that is going to be equal to mu times Fn. Because the system is moving, we know it's moving, that means it will be experiencing the maximum friction force. It's not going to have less because it's already moving. Remember that the maximum friction it's only ever less than maximum friction when the system is at rest and it doesn't need all of the friction to prevent motion. So that's our system. As you can hopefully see, all we really need to do is break down this tension force into a positive, an x and a y component. So if we can figure out Tx and Ty, then we are most of the way there, because once we know Tx and Ty, we can figure out the total tension from those. And we can figure out Tx and Ty based on the friction force and the normal force, because we know net force is 0. So if we know the net force is 0, if F net equals 0, that tells us that Fw, this one here, is equal to Fn, we're just talking magnitudes now, and Ty. Right, we've got those two in the up direction, that one in the down direction. So the magnitude of F weight has to be equal to the magnitude of normal force plus the magnitude of the tension in the y direction. And in the horizontal direction, we have Ff is equal to Tx. Those are the only two horizontal forces. So that is what our system comes down to mathematically. What are all these different values? That's where we need to start applying some more math, mostly vector decomposition, but then a bunch of rearranging as well. So what do we need to rearrange? Let's see. We've got, first of all, let's think about these two Ty and Tx's. We don't know what T is, but we know that Tx is going to be the adjacent one. So that's going to be cosine of, so it's T times the cosine of 18 degrees. And Ty is equal to T times the sine of 18 degrees. Fw is equal to mg. So we've got mg is equal to Fn plus T sine of 18 degrees. And we also have the friction force, which we know is mu times Fn is equal to T times the cosine of 18 degrees. We don't know Fn, but we do know the rest of this thing here. We've got this whole thing here. So what we can do is we can rearrange this one to be in terms of Fn and then put it into this one. The other thing you could do at this point is start calculating these numbers. You know mg, you know sine of 18, you know mu, and you know cos of 18. You could start putting some numbers in. But I'm actually going to keep it as letters, as symbols, rearrange it, and then put the numbers in right at the end. Personally, I find that to be a cleaner approach. There's nothing inherently better about it, but it's just the idea of that generalization. If they then gave us the exact same question with different numbers, I'd already have the formula, and I'd be able to just use the different numbers and calculate the answer. So we've got Fn is equal to mg minus T sine 18 degrees. And now we can put this in place of this Fn. So we get mu times mg minus T sine 18 degrees is equal to T cosine 18 degrees. And now we can just rearrange this because we want T equals. We know mu, we know m, we know g, we know 18. I should have really kept that as theta if I'm sticking to my guns about having symbols and not numbers. We don't know T, and that's what we're looking for, but we now know everything else in this formula. So that means that we're on the last step of this process. We're not going to need to substitute in anything else. We're just rearranging. So we have, let's expand this bracket. We have mu mg minus mu t sine theta is equal to T cosine theta. Let's pull this whole thing over to this side. We get mu mg is equal to T cosine theta plus mu t sine theta. Now we can factorize T out. So mu mg is equal to t of cosine theta plus mu sine theta. I would expect you to be able to do this sort of math. Again, this question is probably a bit harder than what you'd normally be given. We'd normally break it down a bit for you in a test or exam scenario, but there's absolutely nothing stopping you being able to solve a problem like this. Then we can divide by this whole bracket on both sides. So we get that tension is equal to mu mg divided by cosine of theta plus mu sine of theta. And that is our whole answer in terms of the variables, the values that we're given, we can now put in and calculate an answer. So mu was given to us as 0.11, the mass was given to us as 15, we know gravity is 9.8, going to divide by the cosine of 18 degrees plus 0.11 again for that mu showing up again, times the sine of 18 degrees. So we can then do that calculation, and I did do this one beforehand, and it comes out to 16.415 newtons. Feel free to verify that, and we would then present that as just 16 newtons because all our inputs were only given to 2SF, so we would only want 2SF as our output. So again, what you'll see is that the physics, thinking about the system, was really the only way to get there for that problem. If you didn't think about the system, didn't think about that tension, you might just fall into the same trap of thinking normal force is equal and opposite to weight force, and that's going to steer you completely wrong, because then the tension force has to have zero vertical component, but it has to have some horizontal component to cancel out the friction, and it's got to do that while it's at 18 degrees, and that's not going to work. It just makes it physically cannot happen that way. So thinking about the system and all the forces involved was the only way to really catch that little, not trick, but that little slight deviation from what we normally see, in that the normal force wasn't equal and opposite to the weight force because we had this tension force providing some vertical component. So that is the end of example 3. There is one more example for us, so let's go back to the slideshow. A skydiver experiences a drag force of F drag equal to negative BV. You'll notice I've drawn vectors on those ones again. They come and go, right? You need to be used to interpreting equations with and without those little arrow symbols. So we've got the drag force given by negative BV. We're not told what B is until part B. We're told to use the given value. But to start with, for part A, we're asked to determine a formula for the diver's terminal velocity in terms of B, G, and M. And then part B, we're given some values for B and M. We already know G, and we have to calculate that terminal velocity. And the last one is to then think about what happens if the parachutist opens their parachute. So a bit to take on board, let's jump over to the document camera. This question will actually be quite short. First of all, write down the equation we're given. F drag is equal to minus BV. That tells us that whatever the velocity is, the drag is negative B times that. The negative is just telling us that the drag is going to be upwards if the velocity is downwards. Right? That's all that negative is telling us. And that's kind of limiting us to a one-dimensional system, and that's fine. My camera's, there we go, it was out of focus. And that's fine, limiting ourselves to one-dimensional motion, because our parachutist is going to fall downwards, and that's all they're going to do. Right? Until they deploy the parachute, and then they might start traveling in circles and things. And in fact, skydivers can travel sideways and horizontally and stuff. They can use their friction force to do that. But we're going to assume that everything is purely vertical. So we're going to limit ourselves to one-dimensional motion. That's a one, even though it looks messy. That's a one-dimensional motion. What is the formula for diver's terminal velocity? All right, well, what is terminal velocity? Terminal velocity is when the drag force is equal to the weight force. Because terminal velocity, if you remember from the lecture, terminal velocity is when F net is equal to 0. There's no acceleration left. It's accelerated due to gravity to the point where the air resistance cancels out the weight force and you are left with no net force, therefore no acceleration, therefore you can't get any faster. It's terminal velocity. It's the last velocity. It's as far as you can get. So net force is equal to 0. What are the forces acting on our diver? We have a weight force and we have a drag force. That is it. F weight and F drag. They're equal and opposite in order to give net force of 0. Therefore, the weight force is equal to negative the drag force. That's our answer for the net force. We've been told that the drag force, though, is equal to negative BV. Right, so negative BV, and we've got F drag is negative BV. F weight, we already know, is mass times gravity, but we've been asked to find this terminal velocity. So what is the velocity that makes this equation true? Well, we can just divide by negative B. We get negative mg over v. That is our answer. Terminal velocity occurs when negative mg over b is the velocity. The next question is just, what is that value? So now they say, okay, well, you've figured out that formula. B is 0.7, m is 55. I should put the units on here to be technically correct, and that is kilograms. What is the velocity? I hope you can figure this one out without me. Plug the numbers in and get an answer, and hopefully you agree that it's 770 meters per second. The last part says or describe the forces involved after the parachutist opens their parachute. This comes back to physics again. No numbers, no questions, no maths, just thinking about the physics. What happens when a parachutist opens their parachute? What's the point of a parachute? It's to slow you down. If this parachutist is at their terminal velocity or even any fast velocity, and they then open their parachute, the whole point is that they need to slow down. They need to decelerate. They need to decelerate. Deceleration, if they have a velocity this way, that means they need an acceleration upwards. They need an acceleration upwards, so they need a net force that is in the opposite direction to their weight force. So that means that the F drag must be bigger, possibly a lot bigger than their weight force, so that they then accelerate upwards. So that is the description of the forces. Right? F drag is suddenly much bigger when they open their parachute. And it's suddenly much bigger, therefore it's bigger than the weight force, because it was already the same as the weight force. That's what terminal velocity was. The drag force was the same as the weight force. Now, when they open their parachute, the drag force is suddenly much bigger. We get a net force upwards, an acceleration upwards because their velocity is downwards. That is a deceleration, which slows the skydiver down, and that is what we want to occur with a parachute. That's the point of them. So that is the end of this lesson. There is a review on, I'll jump back to the slideshow just for that review slide. And that is just a reminder that there is no step-by-step guide for all physics problems. It's not going to happen. You need to think about it. That is what learning physics means. Thinking about a problem, understanding what's going on, and using that to figure out how to solve any questions. As you're doing that, make sure that you're thinking about everything about the scenario. Think about defining a frame of reference, an origin. What are the laws and equations involved? What are your dimensions? Is it one-dimensional, two-dimensional? How many different periods or stages are you going to divide your scenario into? Is it moving? Is it not moving? Has it got constant acceleration? All of that. Right? There is so much to think about, and that is all physics. That is what the physics is. It's only once you've done all of that and you've figured out all of that that you can jump to the maths and solve the maths problems. And if you try and do that straight away and you haven't done all of that physics, then you're going to fail. You're going to, not the course, you may, but you will fail to solve the problem. And of course, that is the goal of the physics.